Hello there, Mr. Sutton with the AB Calculus 612 Extra Practice number 2 solutions on area between curves. For this problem, we want to, without a calculator, figure out the area between 4x cubed plus 2 and the x-axis between 1 and 2. So for this one, let's first consider whether or not we need to worry about absolute value and things like that. 4x cubed plus 2, that's a cubic function, but between 1 and 2, this thing has all positive values. So we can say that on the interval from 1 to 2, this is positive, which means we don't have to worry about absolute value. Between 1 and 2, 4x cubed plus 2 is always the quote-unquote top function when compared to the x-axis. So I won't worry about any absolute value. Let me just go ahead and take the integral from 1 to 2 of this function here. So I'll need my antiderivative. This bumps up to x to the 4th. Dividing by 4, we have just x to the 4th plus 2x evaluated from 1 to 2. So this is both of these things with 2 plugged in minus all this stuff with 1 plugged in. This is, let's see, 16 plus 4 is 20. This is 1 plus 2, which is 3, so we're subtracting 3 for a grand total of 17. Choice D. For this problem, we have this figure with region A bounded by the x-axis, y-axis, and this sine of x over x graph here. And let's see, the vertical line, oh yeah, k. If k, this vertical line, or the value of the vertical line, the x value, is increasing at a rate of pi over 4 units per second, how fast is the area increasing when k is pi over 6? So we have different rates of change going on. This is definitely a related rates problem. We need to start, though, with an equation that ties everything together. So that equation, I think, would be the area equation for this region here. So we can say that area equals, I'll call the variable a here, and that's going to be an integral from 0 to k, whatever k is, of, well, top function minus bottom function. So this is going to be sine of x over x minus just 0, so sine of x over x dx. And now I need to take the derivative of this whole thing. Okay, so if I take the derivative of a, I've got dA over dt. And taking the derivative of the right side of the equation, we're just using our first fundamental theorem of calculus, where you take the derivative of an integral with a variable in the upper limit. So we're essentially plugging k in for all of this stuff, and also considering the chain rule. So the first thing I'm going to get is just sine of k over k. However, k is its own kind of inner function when you're implicitly differentiating all this stuff. So we also have a tail of dk over dt to consider. So what are we looking for, and what do we have? Well, they wanted to know how fast the area of A is increasing. So that's dA over dt. We actually already have that isolated. So that means we need to plug in stuff for k and dk over dt. This whole fraction here is its own kind of thing that we have to put something into. So do we have a k value? We do. K is exactly pi over 6 at the moment this problem is happening. And how about dk over dt? Well, they told us here k is increasing at a rate of pi over 4. So this is pi over 4 right here. So we can rewrite all of this as sine of pi over 6 times pi over 4. Now we have to simplify this. Now this was a calculator problem, so although you could use your unit circle knowledge and some reducing and all that, I'm actually just going to go ahead to my calculator and plug all this in. So to do this, I'm going to use my good friend Francie fraction, so alpha y equals, get my fraction, and I've got sine of another fraction, pi over 6, so pi over 6, great, close that parentheses. Down here, I'm going to put another fraction with a pi over 6. So here's pi over 6. There we go. And over here, I'm going to put a parentheses. And in there, I'm going to put another fraction with, now this time I've got pi over 4. Close my parentheses. Enter. 0.75. Great. And I know that's equivalent to 3/4, so choice B. For this no calculator problem, we wanted the area of the region in the first quadrant bounded by e to the x over 2 and x equals 2. So the first thing to note here is that e to the x over 2, an exponential function, is positive like everywhere, including from 0 to 2. So because this is positive everywhere, that means when we set up our integral and do top function minus bottom function, this is going to be the top function because the only other function here is basically the x-axis. All right, so I'm going to have an integral from 0 to 2 of, well, just this, e to the x over 2 dx. Because this is a no calculator problem, I now have to take my antiderivative and evaluate this with my fundamental theorem. So antiderivative of this, we're going to have e to the x over 2 divided by the tail, so multiplying by the reciprocal then of 1/2, which is 2. That's going to be 2e to the x over 2, evaluated from 0 to 2. So this is 2e to the 0 over 2, or actually 2e to the 2 over 2 minus 2e to the 0 over 2. That's going to just be 2e minus, well, this is just 2 times 1. So 2e minus 2. Do we have an answer choice for that? We do. Choice A. On this no calculator question, we need to find the area enclosed by x minus 2x squared and negative 5x. So to do this, we first need to figure out where these intersect. So I'm going to set them equal to each other and solve for x. Let me add 5x over to the other side here. So that's 6x minus 2x squared equals 0. And now I'm just going to factor out a 2x. That leaves me with 3 minus x inside. So then I have x values of 0 and 3. Great. So at this point, it's time to set up an integral from 0 to 3. And because I don't know which of these functions is the top value between 0 and 3, and I don't feel like figuring it out, I'm going to use absolute value around my integral. So I have absolute value of integral from 0 to 3 of, well, this function minus this other function, which is essentially this 6x minus 2x squared that we got when we zeroed out our equation. So all that goes in my integrand. Now I have to take the antiderivative of this stuff. So that's going to be, let's see, this bumps up to a 2, so that's going to be 3x squared minus, this bumps up to a 3, so we have negative 2/3 x cubed, evaluated from 0 to 3. So I've got all this stuff with 3 plugged in, minus all this stuff with 0 plugged in. And again, this absolute value is hanging around because I don't know if this is all coming out positive or negative. So in this first one, we've got, let's see here, this is 27, and this is 2/3 of 27, so that would be 18. So 27 minus 18. The rest of this is just 0. And this actually comes out to a positive number on its own. So this comes out to 9, which gives us choice D. On this no calculator problem, we want the area of the region bounded by this polynomial and the line y equals 4. So to figure out that region, we need limits of integration, which means we need to know where these two functions actually intersect. So let's set them equal to each other. And now I'm going to go ahead and solve for x. To get this, I'm going to subtract all this stuff over to the right side, just so I get a positive x squared. So I'll have an x squared, a negative x, and 4 minus 6 is negative 2. All of that equals 0. And now factoring this, two things that multiply to negative 2 and add up to negative 1. That's positive 1 and negative 2 inside parentheses with my x's. So that means that x equals negative 1 and x equals 2 are going to have to be my limits of integration here. Now, I don't really know which of these functions is higher up on the interval from negative 1 to 2. I suspect it's going to be my line because this is an upside-down parabola. Actually, so the upside-down parabola should be higher up. Either way, I'm going to use absolute value so I don't have to worry about that. So I'm going to have absolute value of the integral from negative 1 to 2 of the following. So basically, I need one function minus another. And it doesn't matter what order I do this in terms of correctness because I have absolute value to take care of the mess at the end. However, I'm going to do this expression here, x squared minus x minus 2, because that was 4 minus this other function. So it is one subtraction here. And it's got a positive x squared, so I kind of like that. All right, going through and taking my antiderivatives now. We've got 1/3 x cubed minus 1/2 x squared minus 2x, evaluated from negative 1 to 2. So that's all of this stuff with 2 plugged in, minus all of this stuff with -1 plugged in. And I got to be honest, if this were a free response problem, I'd be stopping here because you don't need to simplify for those. However, it is multiple choice. We need to pick one of these, so we're going to need to do the arithmetic here. So going through one term at a time, this first one, this is going to be 8/3. Still have that absolute value. And then this is, let's see, -1/2 times 4, so that's -2. Next, -4. And now we're going to have to negate all of this stuff that we end up getting. So this is initially -1/3, but the negative makes it a +1/3. This is initially -1/2, but now it's +1/2 with the negative out there. And this is initially +2, but this negative makes it a -2. Next up, I've got to add all this stuff together, which is kind of annoying because we've got fractions and they don't even all have the same denominators. Some of them do, though. For example, 8/3 and 1/3, that adds up to 9/3, which is just 3. And now let's do the whole numbers here. -2 minus 4 minus another 2, that's -8. And then finally, we have this 1/2 kind of hanging around. So this is -5 plus 1/2. That would be -10 halves plus 1/2, which is -9 halves. Absolute value cleans up that mess and gives us just +9 halves for our area. And we can finally pick answer choice C. On this calculator question, we want to find the area enclosed by these two polynomials here. So I first need to start by figuring out where they intersect. And just so I don't have to keep rewriting them, since this is a calculator problem, I'm just going to rename them. This cubic one I'll call f of x, and I'll rename this other one to be g of x. So I need to figure out where f of x equals g of x, where these intersect. I'm going to go to my grapher for that. So here we are. I got y equals of these things. Let me just do zoom 6 because I don't really know where these are going to intersect. So this is usually a pretty good place to start. And it looks like we've got a couple intersections here. We have an intersection right here and another one right here. And that's going to be it because this is a cubic function, so you're not going to be crossing too many more times. Let me zoom in a little bit here. Let me change my window up. So let me see. This is about, let's see, 5, 6-ish. Let me do my window between 0 and 6. And then zoom fit for this. I just want to have a nice clear picture, so it makes it a little bit easier for me to go ahead and find those intersection points. Well, that's no clearer than before. Let me change that back to be, let's see, 5 for my upper bound. All right, let's try this out now. All right, that's a little bit better. So now I can clearly see those intersection points. So let me find all of them. For the first one, let's do, let's see, second trace and intersect, option 5. Move my spider over here. Enter, enter, enter. It's actually exactly 1. Well, that's nice. All right, let me find the next one here. So second trace, intersect again. This next one, enter, 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 is 2. Wow. All right, how about that last one? That last one kind of looks like 5. So second trace, option 5. Let me go all the way over there. Wish my spider moved a little faster, but hey, I'll take what I can get. Enter, enter, enter. And that's an intersection of exactly 5. All right, well, we don't have to store any values, I guess. So we can say that these equal each other at 1, 2, and 5. Now, one way to do this would be to do 2 separate integrals. First integral, you could have f of x minus g of x from 1 to 2. Your other integral would be from 2 to 5, and that would be g of x minus f of x because the line is the top function in that second place. A faster way to do it would just be to take the integral from 1 to 5 and take the absolute value of f of x minus g of x. So integral from 1 to 5, absolute value of the difference of these two functions. And you actually could also do g of x minus f of x. It doesn't matter, I guess. But anyway, absolute value, you're forcing every single distance strip out of this to be positive. I'm going to do that on my calculator. So let me quit out of this graph because I don't need it anymore. And let's see here. I've got Math 9, integral from 1 to 5. And in here, I'm going to do absolute values. So let me do alpha window. That'll let me pull my absolute value out of there. And then alpha trace y1 minus alpha trace y2 dx. Press enter and let the calculator do its thing. 11.833. All right, I'll take your word for it. That's going to be choice B. For this problem, we have the graphs of the function g, this curvy thing, and the line y equals x shown in this figure. And they're telling us these intersect at the points 0, 1, and 2 for x values at least. We want to know which expression or expressions gives us the area enclosed by these graphs. So because we're changing which function is the top minus versus bottom, we can't just do this with straight up integral from 0 to 2 of, for example, g of x minus x. So that's why these answer choices all look kind of weird. Let's go through each of them and see what they're actually doing. For this first one, we're doing the whole integral 0 to 2 x minus g of x, and then we're taking the absolute value of the result of all that. So the absolute value is a good thought. Unfortunately, it's happening too late here. By the time this absolute value happens, the negative and positive area you would get from doing x minus g and g minus x, those have been added together already by this integral. So we need the absolute value to happen a little bit sooner. For this next answer choice, we're taking the absolute value of the integrand itself. So that means whether we're doing x minus g or g minus x, either way, whichever one is negative, it's always becoming positive. We're always getting positive distances out of this situation, and then just adding all those positive distances together. So since our distance is always positive, this is a big yes. This one will actually give us the area enclosed by these curves. Awesome. And then there's this last choice. This one, they've actually split the integral up. We've got one integral from 0 to 1 of g of x minus x. So here's g of x. Here's x. We're doing top minus bottom from 0 to 1, so that's good. The next one, we're going from 1 to 2 and doing x minus g. So from 1 to 2, x minus g, we are again doing top minus bottom. Since we're consistently doing the top function minus the bottom function, we're consistently getting positive area out of this, so this is another yes. Looking at our answer choices, we want the one that has options 2 and 3. That would be choice D.